Hello 5480 students. So this video is for if you're in my 7th or 8th period class, the 5480 class. So let us take a look at Unit 7, Electrical Circuits. This setup at the beginning is a little bit different than it is in other units, so I just want to point out how this works. So over here with the objectives, this lists all the things you should be able to do in a specific section. On page 1 then, this hits on all of the topics you need to be able to do. So for instance, you should be able to tell me what current means. Current is charge over time. Think of it as like the rate charge flows. But current is also dependent on the voltage of your source and the resistance of the resistors connected to it. So I would read through these objectives first, then see if you can do all the things. So let's start there. I want to calculate the resistance of this wire. I know the voltage and current have a direct relationship because of Ohm's law. If I write down Ohm's law equation, that's current is voltage divided by resistance, I can pick any point along this line, so I'm going to pick this one, and use this data point to calculate the resistance of the wire. So the current was 2, the voltage was 8, and cross-multiplying here, this means the resistance is 8 divided by 2, or 4 ohms. Pick any point, except for 0, 0, obviously, and apply the Ohm's law equation. Next, draw a line for a wire with twice the resistance. Well, if it had twice the resistance, it should have half the current at every data point. So at 2 volts, it would only have 0.25 amps of current. At 4 volts, it would only have half an amp of current. Repeating this over and over, and all the way up to 12 volts, resulting in only 1.5 volts or 1.5 amps of current, I see that my second line, the wire with twice the resistance, has more resistance and therefore less current than the original. Now, current of 3.5 amps, what does it mean? Well, 1 amp is equal to 1 coulomb of charge passing through a wire in 1 second of time. So if you picture our wire and charge is passing through that wire, right? Maybe it passes through this area. This must mean there are 3.5 coulombs of charge that flow through the circuit every second. I think the first two choices make sense because they're both dealing with charges moving over time. The last two definitely don't because those deal with energy, and energy is not related to current. But it's not individual electrons. Individual electrons are too small. You'd have like billions upon billions of electrons per second. So we do with coulombs of charge per second. So that's why I selected this choice. Now, how much current is there? If I have 3.5 amps of current, think of this as I have 3.5 coulombs of charge flows through every second. So after 1 minute of time, I would have 3.5 times 60 coulombs of charge, or 210 coulombs. If you want, we can use this equation. We can use the current is equal to charge over time, and I used it this time to solve for Q. Q is my charge in coulombs. I multiplied current in amps times time and seconds to get coulombs of charge. E, which one of the following statements about DC circuits is false? Circle 1. Current is protons flowing from the positive end of the battery to the negative end. Well, that's easy. That's already my false one. I know that the protons don't flow when we talk about electrical currents because remember, protons are heavier than electrons. They're bound in the nucleus. They're not going to move, right? So let's see, let's just double check and make sure the other ones are true. So is it true that electrons flow from negative to positive? Oh yeah, it is. Is it true that the charges move very slowly? Yes, a key vocab word, one that people often overlook, is the speed of an electron is called the drift velocity, and it's very slow, about a millimeter per second. But the energy flows with the electric field, and that's super duper fast. The energy is carried by the electric field at nearly the speed of light. So those are true. So the electrons themselves move slow, that's their drift velocity, but the energy moves fast. Finally, let's do some proportions. Ohm's law says that current is proportional to voltage over resistance, and my original current is 12 amps original. Well, what would happen if I doubled that voltage? Well, that should also double the current. And hey, if I decreased the resistance, that actually should make more current because I'm dividing by a fraction. Dividing by a fraction is the same thing as multiplying by the reciprocal. So what this statement says is the new current is 6 times bigger than the original current. Notice this little neat substitution thing I do here. My original current was 12, so I'm going to replace this number with a 12. My new current is 6 times bigger than the original 12. 6 times 12 is 72. My new current is 72 amps. Ta-da! So, we did graphical and mathematical models. We found simple current, voltage, and resistance. We did resistance from a graph. We talked about flow of charge versus flow of energy. We talked about the unit for electric current is amps. Ooh, here's one we left off. Why are some materials conductors and some insulators? Remember, conductors are the ones with loosely bound electrons. That's why the electrons can go wherever they want. And insulators are tightly bound electrons. Insulators don't let electrons flow freely because they have too many bonds. Okay, so let's see page number 2. This is talking about electrical resistance. I'll put in more detail when I write out the formal answer key to this, but for the video, I'll explain these in words. The wire with the greater resistance is A, because the longer the length, the more the resistance. This was one of the first experiments we did in this unit. A longer wire has more resistance because it has more distance the electrons have to move. Imagine if my electrons only had to move from here to here. Well, that's easier. It's like running a shorter distance versus running a farther distance. So wire A has more resistance because it's longer. The electrons literally have to go through a longer distance. Now let's say I have 2 wires of equal length and different thicknesses. That changes the cross-sectional area. And I remember from our lab, one of the first labs we did in this unit, as area increases, that gives more space for the electrons to move. And if you're wondering what area, I mean this area, the circular area at the end of this wire. Because this area is bigger, this makes it easier for electrons to move through B than it does for A. Because the area is bigger for B, there's more space. Because electrons have collisions with each other, ultimately causing resistance, those have fewer collisions because it has more space for electrons to move. B. Metals are good conductors of electricity because their electrons are loosely held. Remember that from page 1. Electrons are loosely held. So now let's do 2 more proportions practice. A wire has an original resistance of 10. So I'm going to write my original equation. That's resistivity, L and A. That equals 10 ohms. That's my original. Then we take this long and skinny wire and we fold it over 3 times. So it has 1/3 of the length, but 3 times the area. I'm trying to keep the area the same. There's my length. This path is easier for the electrons to go on, so I'm expecting a smaller resistance. The resistivity, that's the material, stays the same, but the length is smaller, that decreases the resistance, and the area is bigger, that decreases the resistance as well. The new resistance is 1/9 of the original. Notice that fancy substitution here. If my original resistance was 10, then rho LA equals 10. 1/9 of the original 10 would be 1.1 ohms. It's much, much easier to get through this arrangement because it's both wider and shorter. Now, this is the same type of proportions, and if I'm having you do it a bunch of times, it's probably a pretty good indication you know what we're going to do with this. So now the wire is replaced with a completely new material and has twice the length. So the original resistance was 12. The new one has the same resistivity, so same material, twice the length. Oh, sorry, I said that funny. Has twice the resistivity, so a larger resistance material, twice the length, and the same area. Regrouping this, I see 2 times 2 is 4, 4 times the original 12 ohm resistance. So if my original rho LA was 12, I'm replacing that with my 12. 4 times 12 is 48 ohms. Let's write that right, 48 ohms. So on here, we know electrical resistance comes from collisions. We know that resistance depends on area, length, and resistivity, and we know that some materials are conductors and some are insulators. Yay! Checks. Now let's go on to resistors in series. You should be able to describe a series arrangement, calculate its equivalent resistance, determine the voltages and currents. The equivalent resistance in series would be just adding them all up. The currents are the same for everything in series. So all that's left is using Ohm's law to calculate voltage. Let's try series circuits. And what I'll do is I'll start showing my work down here and then use that to start filling in the chart. You'll see like the logic here. Plus, hint, I will ask these in a logical order so that you're not just like filling out the box and then having to write a bunch of extra things. So first, A, draw the direction of conventional current. Conventional current starts from the positive terminal of the battery, then goes to negative. Conventional current is positive to negative. Next, let's get the equivalent resistance in box H. Because this is in series, R equivalent is R1 plus R2 plus R3. That's equal to 2 plus 3 plus 4. That's 9 ohms of equivalent resistance, and I know that it's because it is in series. How to get total current then? Across every row, Ohm's law has to work. So I'm going to write Ohm's law because that explains my math here. Ohm's law can be written as voltage equals current times the resistance in every row. So that's 18 equals I times 9. Dividing the 9 to the other side, current is 18 divided by 9, or 2 amps. Once I know that this is 2, I know that all the other currents are 2. Because in series, the currents are the same. So same in series. So now that we've got that, let's explain how to calculate box C. That's the voltage drop. Think of that as kind of proportional to the energy that resistor uses. Since across every row, Ohm's law requires that voltage equals current times resistance. The current of 2 times the resistance of 3 gets a voltage drop of 6 volts. So I'm going to go repeat that all up here. So 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, and hey, just as a check, 4 plus 6 plus 8 is 18. This is a check. This actually has a different pattern that you and I won't be working with. But as a check, if you want to see if you've done it right, these should add up. All right, so let's talk about power and energy. Power is current times voltage. It is the rate that electricity is transformed into other types of energy. So the current of 2 amps times the voltage of 18 gives me 36 watts of electrical power. 36 watts tells me that 36 joules of energy is transformed into some other form each second. So energy is power times time. I take my 36 joules per second, that's 36 watts, and I'm going to take 15 minutes worth of seconds. So hey, that is 900 seconds. 36 times 900 gets me 32,400 joules. Joules are a very small unit, so when you do your math, expect a lot of them. Now, notice if you added another resistor in series, let's say you added another one here, that would increase the equivalent resistance, but decrease the current. That actually lowers the power in the circuit. That's why when you added more light bulbs in series, your circuit got dimmer and dimmer and dimmer. Not the same for parallel. So let's do the parallel one. First, it says draw the direction of electron flow. An electron flow goes from negative to positive. Write that on your sheet if you didn't already. Don't count on you to just remember it like several days from now. So electrons flow from negative to positive. They also flow around each of these paths in the same direction. So now I can watch my currents as they make these loops. So let's get equivalent resistance first. This is the equivalent resistance of something in parallel. So I'm going to pull out the parallel equivalent resistance equation. Make sure to write the equation down first. I know I say it a lot, but I also take off points for you, like a lot. So write down this equation first. That's a point. Then start plugging in the numbers. If you just start plugging in the numbers, there is a chance I don't know what you're trying to do with them. I'll be like, oh, so you divided. Did you do that randomly or did you mean to? So now I'm going to take my 24 plus 8 plus 12, and I'm going to invert every one of those terms. Use my invert button here. So inside the parentheses, I should see 0.25. But I still need another set of parentheses and invert That gives me an equivalent resistance of 4. As a check, my equivalent resistance in parallel has to be smaller than the smallest resistance. So is 4 smaller than 8? Yeah, that means I'm on the right track. Great, so now let's get the current. I'm going to do this with Ohm's law across that row that says voltage is current times resistance. You could alternately write that as current is voltage divided by resistance. So 24 volts split up over 4 ohms of equivalent resistance gives a total of 6 amps of current. If this is 6 amps, I don't want you to go like make all these 6, because remember, this is parallel. And the parallel rule says our voltages add up. Or sorry, voltages are the same. I said that wrong. Voltages are the same. That's our parallel rule. So how I get my voltage drop for box E then is these are all 24, because items in parallel need to have the same voltage as each other. Next, how did you calculate box D? I used Ohm's law again. Surprise. Ohm's law says that current is voltage over resistance. So if the voltage was 24 and the resistance was 8, that should give me 3 amps of current. Now let's repeat that. We'll do that for the rest of them. 24 divided by 24 is 1. 24 divided by 12 is 2. And just to check, because we didn't do the Kirchhoff's current law, these should add up. So even though we didn't talk about this law, does 1 plus 3 plus 2 equal 6? Yes, we got it. Good. Okay, so how is this like a household circuit? How is it not? Household circuits, you must know this, are in parallel. They are in parallel because in parallel, each one of these can have their own branch. So if one of them goes out, the current continues to flow through the rest of them. So this is like a household circuit that's in parallel, but it is not like a household circuit because this voltage is wrong. If this was a household circuit in the US, this would be 120 volts, and it would be an alternating current. So I'd be drawing a symbol with like the circle and the Pepsi sign. Down at the bottom, if I added a 4th resistor, how would the circuit change? If I add a 4th resistor here, and I'm going to write out the symbols and come back and write the words out later. For every additional branch that I add to this circuit, my equivalent resistance decreases. That makes my current increase. And that's kind of weird because then that means adding more resistors creates less resistance. But that's because every time you have more resistors, you also have more paths. That makes it easier for the electrons to flow, so you get more current. So equivalent resistance decreases, current increases. So let's check. We've done the series one and talked about how series has the same current and equivalent resistance, you add them up. In parallel, we know that the voltages are all the same. And equivalent resistance, we use our inverting equation because equivalent resistance should get smaller and smaller with each branch. We talked about what happens if you add more resistors, that the current increases and power increases. So now let's go to schematics and circuit logic. Be able to draw a circuit diagram. Tell apart open, closed, and shorts. Describe why a short circuit is dangerous and where to put a fuse to protect your circuit. So first off, let's draw a circuit. So I want 3 batteries. You want 3 long symbols and 3 short to show 3 batteries. And it is convention that if you know the total voltage, to label that. And I do. The total voltage is 1.5 times 3, or 4.5. Because it doesn't specify, you can connect these in any order. It doesn't have to be series or parallel. I just picked series because it didn't specify. 6 ohm light bulb, 2 ohm resistor, and an open switch. But then it asks for direction of electron flow, which is kind of silly because this is an open circuit. If it is an open circuit, then there is no electron flow, so I'm not going to draw it. Just in case there was, though, because I was obviously getting at the idea that electrons flow from negative to positive, the current of electrons would be flowing clockwise, from negative to positive. All right, so now we got this circuit. If bulb A is removed and not replaced, imagine this gets taken out and leaves an open path right here. Just like in this problem, an open path means no electrons are flowing through this path. But hey, that still allows us to have current here. The conventional current would go from positive to negative. So from here, the long terminal is positive. Even if that broke, I'd still have current. So all the other resistors would continue to stay on because current continues to go through the other unbroken branches. The two circuit elements that have the same current with each other are in series with each other. That's C and D. They're along the same path. That means B and A must be in parallel with each other. And I can see that they are because they have current split up over 2 paths. Parallel is 2 paths, series is 1 path. Okay, next, draw a fuse on the diagram that would prevent a short circuit. I want to draw my fuse adjacent to the power supply. There's a reason that circuit breaker box is near the main electrical for your house. You want to be able to stop all the current at its source, so your fuse should always be next to your power supply. Now, how does a fuse keep a current or a circuit safe? Is a fuse melts and creates an open hole in the circuit. It melts if there's too much current, preventing electrons from going through, so that other items in the circuit don't burn out or light on fire. Which leaves my last problem. Problem 6, electrical power and energy. I want you to be able to solve current for household circuits, for power and resistance, calculate energy in kilowatt hours, describe that household circuits are in parallel because they each have independently running branches, and use that to find power and resistance of a group of appliances. That last standard's on there twice, don't mind me. So I already explained this 2 times, I'll explain it one more. The appliances in your home are in parallel because each one of the branches is going to operate independently. So if the 30 ohm resistor failed, the 1400 watt microwave would continue to operate. Calculate the current through the blender. Current is actually in 3 different equations, but most often we use Ohm's law. Current is voltage over resistance, so 120 divided by 30 is equal to 4 amps. But current through the microwave, I don't have the resistance. I have the power. So I want to pick out the equation that has power and current together. That's P equals IV. The power is 1,440. The current is what I'm looking for, and the voltage is 120. Dividing by 120 to the other side, 1,440 over 120 equals 12 amps. And I'm going to draw these together. So let's say that my blender, that's this one, has 4 amps of current. And I'm going to draw it conventional, this way. Then my microwave has 12 amps of current. At that junction, if 4 amps goes in and 12 amps goes in, that must mean 16 amps runs total. So question, is 16 amps enough to melt a 15 amp fuse? It is, because a 15 amp fuse melts if you have any current 15 or higher. So if you have a 16 amp current that's about to go through this fuse, then that melts. If both of these appliances are on at the same time, the 16 amp current will melt the fuse and turn the circuit off. So let's say I'm smart and I only operate one of these at a time. The blender had a current of 4 and the voltage was 120. So it has a power of 480 watts. 480 joules pass through every second. Now, the energy per day is really only in 5 minutes of time, according to this right here. So when I do energy as power times time, I'm going to take watts times 5 minutes worth of seconds to get my ultimate number of joules. So that's 480 times 300. Big number, 144,000 joules. So if I want energy in joules, I need to use watts and seconds. If I want energy in kilowatt hours, then I need to use the same equation, but change my power to kilowatts. And my time is already in hours, so no conversions needed. Remember from above, the microwave had 1,440 watts. Well, that's only 1.44 kilowatts. And that makes my math a lot easier, because then I'm just doing 1.44 times 16. And 23.04 is a much easier number to work with for me than 144,000 is. Finally, a bonus. If each one of these units costs 27 cents each, how much does it cost to run this microwave? Remember, cost, you're taking how much does each unit cost, right? So it's 27 cents for each of these kilowatt hours, and I have 23 of them. Multiplying this together, I take my previous answer times 27 cents. So it cost me $6.22 every month to run my microwave. Dude, assuming I actually run a microwave for 16 hours, that seems like a gratuitous amount of microwaving. But who knows? Maybe I really, really enjoy microwaving. All right, so review this one more time. Make sure what you have on your notebook or in your note sheet makes sense to you. You're the one who has to read it. You're the one who has to answer questions. So make sure it makes sense to you, and good luck.